Hey guys, welcome back to another episode of Introduction to Computer Networks at NTU. This is again Polly speaking. Guys, this is week 11, episode 20. That is also saying that exam 2 is coming up tomorrow. Okay, and because of exam 2, this week we have only 2 quizzes due. And both of them are straightforward, and we'll complete them today in class. And hi, Gao Pu. And you know what? And that's all we need to say about the announcements. Except maybe that's clicking to exam 2 channel. How about that? I see that more of you popping up today, probably because exam 2 is coming up tomorrow. So why don't we go through the things that I have announced about exam 2. Okay, so first of all, you will see from exam 2 channel the exact date and time for the exam and the exact scope for the exam. Note that PA3, although it's within the scope of exam 1, but it would be included within the scope for exam 2 as well. So you'll be writing the client program as well as the server program, guys. And textbook-wise, the scope is chapter 2.6 all the way to the end of chapter 3. And today we're going to start talking about chapter 4, so it's not going to be in the exam. So if you are really short of time preparing for the second exam, you're free to go. And by the way, guys, exam 2, the average score is typically significantly lower than exam 1, because exam 1 is about the most basic chapters. And all we talk about there are very high-level overviews of the internet and the application layer protocols, which you guys are somewhat familiar already, right? And if you recall chapter 3, it's transport layer. And we spend most of the time talking about this RDT, reliable data transfer mechanism, and the congestion control mechanisms. Okay, so those are more technical with complexity. Things are straightforward, but you need to make sure that you understand the interaction between the client-side server side, or sender side, receiver side. Okay, so it's straightforward, but there's the dimension is higher, and there's interaction of multiple parts. So that makes it a little bit complicated, challenging. All right, and regarding the exam rules, everything remained the same as exam 1. So you recall, for the exam 1, you want to come a little bit earlier so that Polly can check your photo ID. When the whole class is checked, then we start taking the exams. And you see that Polly would also remind you about the time. And when there's only 10 seconds remaining, any updates, editing after that is your own risk, is on your own risk, all right? Because the penalty of turning something late is severe. And so you probably want to close everything at the last 10 seconds. And for the exam date, same. You want to join this Google Meet session and stay on for the entire time of you taking the exam. Just like exam 1, if you manage to finish the exam earlier, you are free to go, but let Polly know. Okay? And the Google form, the exam form will be, the link will be available here an hour before the exam, okay, the latest. Guys, you will need an account individually for the PA related problems. And those accounts are, again, available. So it's, again, your student ID being the username, and the default password is ep20. So, guys, log on and change the password as soon as you can. All right. And so similarly, in addition to going back to channel exam 1 and go through the exam process, exam rules, you may also go to the exam page. We went through the exam page in detail for exam 1. So you just try to go back there and read the rules, cautions, and remind yourself, okay, what you need to be careful about. Now, something a little bit special for exam 2 is this. For exam 2, the PA-related problems will involve you guys writing your own server. you see now, you understand now. For your server to run, you need a unique port number. Otherwise, you will have what? Conflict with other students' server. So, guys, when you are testing your server, make sure that you run it on the port assigned to you. And that port assignment is available from this link here. Okay, it's called the e2 port assignment.pdf. If you click into this link, then you should see that next to your student ID, that is the port that's assigned for you during the exam. All right, and I see more of you popping up: Josephine, Sam, Caesar, Ivan, Kaijin, Ricky, and Eric. Okay, good to see you guys all. And you guys are right on time hearing Polly explaining how exam 2 is going to be like. And guys, exam 2 is generally more challenging than exam 1. So if you feel a little bit more frustrated, if you need more time for exam 2, that is completely normal. And this is just so that you can stay emotionally stable through the exam. So take things easy. Take things easy. And I hope that exam 2 is selected at the time that you are done with most of the midterm exams, and it's also before the pressure of final exams are here. So yeah, that's probably the second most challenging exam. The last exam, some students take it harder, but some students actually find the last exam easier. So the third exam, typically I see that some students did exceptionally well, but some students less. So third exam is often very interesting, and the average sometimes can be higher than exam 2, but sometimes lower than exam 2. Okay. All right, now let's go back to the lecture today. Again, as I mentioned, we are gonna introduce chapter 4. All right, in fact, chapter 4 and chapter 5, they are actually together describing two very important functions in the network layer. So exam 1 is overview and application layer. Exam 2 is transport layer. Now we are in exam 4 and 5, network layer. All right, and so in the overview video, you will see that what the network layer does, essentially, the segments from the transport layer, when it arrives at the network layer, it will be broken further into datagrams. So we add another header called the network layer header, recall? And these are datagrams. Okay, so it's part of the segments plus the network layer header that forms a datagram. These datagrams will be passed from router to router. Hey, this time it's no longer from host to host. It's from router to router all the way to the destination. Okay, so at the receiving end, the destination is the receiving end. These datagrams, after the network header is removed, will be reassembled back and becoming a segment and then pass further up to the transport layer. You see, transport layer to the network layer, going through the network, and then from the network layer back to the transport layer. Okay, so in this video, you will hear the function of the network layer, and you will see an animation of a packet going all the way from the top to the network layer, and how they travel the network, okay, to the destination and then pass all the way back to the application layer. In the second part of the video, you will hear two very important functions of the network layer. One is called forwarding, the other is called routing. And no worries, these two terms, they sound very new and strange to you guys. We'll use an analogy again. So that analogy is a bunch of us forming a group traveling to a destination in Taiwan, for example, Kenting. Okay, you see that these data traveling through the network is almost like us traveling physically to a destination in Taiwan. Okay, so that is what this video is about. So you see, the video is a little bit long, 5.5 minutes. Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer: forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host, and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on a machine. Each and every router inside the network here would also have the network layer protocols running. Now, to be exact, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram, and sometimes also called the IP datagram. So transport layer, TCP layer; network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. So at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, datagrams, will go on to the network and travel from router to router. And each of the router will examine something special, in the packet header, in the IP datagram header, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in anime, so packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed, and the segment restored and pushed up to the higher layer. Right, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, yes, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully, it gets to the next router that is appropriate, so we don't take too much time to pass the packets until it reaches the receiving host. The other is this, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to canteen. Yeah, I know the weather is getting warm. It would be really nice if we're in canteen. Well, the thing you need to do first is this, routing. You pre-compute or you Google, and come up with a plan, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take a high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus, or do we all rent a car or rent a number of these bikes so that we ride along all the way to canteen? So the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop and then you hop on the next vehicle taking you to Kenting. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. All right, so forwarding and routing. Forwarding is the things that you do on the day of travel, and routing are the things that you do ahead of the travel. Okay. Nowadays, I see people doing sometimes a little bit of routing on the day of travel. And you see these guys will be, looking things up on the phone and trying to figure out what to do next. But you see that the routing process can be time consuming. And if you do that on the day of travel, you might miss the train or miss the bus that you're supposed to take. And so you might miss the destination, okay, on the day you wish to arrive. So you see that on the internet, routing is typically done way ahead of the travel of the packets. And forwarding is exactly how packets are forwarded, okay, in a really fast speed on the internet today. Good. Next video, let me introduce two terms which you have already heard about: data plane and control plane. So data plane is the space we do forwarding. The router does forwarding. The control plane is the space in the router that does routing. So essentially, data plane, chapter 4, that handles the forwarding function, talks about the forwarding function. Chapter 5 talks about routing, that is the control plane of a router. All right? So this video will talk about these two functions a little bit more and show how the data plane looks like. And control plane is a little bit bigger, looks bigger, because it usually, to come up with the route, it involves multiple routers doing calculation somehow collectively. And there are two ways of doing such a route calculation. In the older time, the traditional way is actually more distributed. The routers would do computation, not exactly relying a lot upon other routers, but somehow they can calculate the routes. But nowadays, more recent years, we do the route computation in a more centralized way. To your surprise, isn't it? Yeah, pay attention to this video. This is again 5.5 minutes, but very fundamental of what a router does. First, data plane. Second, control plane. And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay? And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay? And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port, and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end to end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay? The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the SDN, we actually ask a couple very powerful machines, okay, a couple very powerful SDN servers that are actually sitting far away from the routers. to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. Okay? So the tables are actually computed on the routers locally, okay, in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. Okay? And it's very simple, very fast. Okay? All that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. Okay? So this is called the fast output interface lookup. Okay? Once we get a match, we get also the outgoing interface. Okay? Let me illustrate. So these are the routers. Okay? And inside the router, okay, you see this is the entire operating system stack. Okay? There's this thing called the forwarding table, and each router will have one of these. Okay? When there's a packet coming in like this, it's going to look into a packet header field, okay, and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. So output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. Okay. So this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, okay, higher up in the operating system stack. To be more exact, okay, and let's talk about the traditional approach first, where the computation is distributed. Okay. So the routing algorithm is going to be running on each of these routers, okay, and up here. Okay, the routing algorithm here, 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 and here. Okay. So each and every router, okay, is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages, okay, between these routing algorithms distributed on the routers. Okay. And this is the control plane. As a result of the computation and exchange, okay, they find out what should be the forwarding table, okay, for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here, because the computation is all where? Up here, okay, a couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is going to provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers. All right, so there's a pop-up quiz today, guys. Polly already typed up on the live chat asking you guys, just reply intuitively. Do you like the traditional routing, which is distributed, better? Or the modern routing, which is centralized, powerful machine, they're calculating the routes for a bunch of routers. Okay, so just tell me which one you like better. All right. Now, due to the time constraint, while you guys are trying to reply and think through the pop-up quiz, let's move on to the next topic, the service models. Okay, and by the way, you see in the topic that I say L3 service models, that is layer 3. What is layer 3? Network layer is layer 3. Okay. For some reason, we just call the network layer layer 3. All right. And now recall a little bit of transport layer. We said that in the transport layer, there are two services model. One is called the connectionless, the other is called connection-oriented. And the one on the internet that is connectionless is what? UDP. And TCP is the connection-oriented one. You know what? Network layer has also two service models. One is connectionless, the other is also connection-oriented. What's very different in the network layer is this. Internet's network layer service implements just the connectionless service model because the network layer function is just forwarding and routing. The designer of internet has decided that we do it the connectionless way, which is the data forwarding way. The connection-oriented one, guys, think of it this way. It's a little bit more like circuit switching network. You establish some sort of circuit, some sort of connection from the beginning to the end. That way you can ensure other kinds of services, for example, a shorter delay. For example, no packet loss. Okay, so internet is the less fancy type of service model. And there are some other designs for building a network that's a little bit more connection-oriented, circuit switching like. And this video talks about these two service models. Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out and the data is just going to arrive. But unfortunately, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. So the service model we'll be talking about next is to talk about how we implement, what kind of channel we're providing here. Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. So you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. And this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, ATM is actually competing with the internet. I think towards late 90s, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old. But these are examples of connection-oriented network layer service. Now, to establish such a connection will involve routers, and the involvement is actually quite deep. It's complicated enough. It's the third important function, in these systems, on top of routing and forwarding. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN, ACK, and then ACK for the SYN, ACK. Hey, that's the establishing connection, right? It sounded very much like these ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things
in the network layer involving the routers.
Alright, so guys, now you see that the internet was designed by a bunch of more free-spirited engineers. And so these legacy technology like ATM, frame relay, they are actually from the engineers who prefer having more control, being able to create something like circuit switching type of service. But internet, unfortunately, at the network layer is connectionless. Or fortunately, it's connectionless. Okay. Before Polly introduce the next video, let's go over what you guys have voted for. Whether you like the centralized, the traditional routing, the distributed one, or the modern one, the centralized one better. So I see here Henderson likes the modern one because it reduces the load of the individual router, right? So the calculation load is on the big server. Caesar also like the modern one because easier to optimize. Indeed, I also like the possibility of you being able to optimize or do finer granularity control of the routes on the network, right? Reprogramming the network, for example. And in case there's a failure, right, you can potentially debug problem, identify where the problem is easier because the central server here has the entire view of the network. And Sherman likes the software one, the SDN one, right? So that's the modern one. And Sam likes also the centralized one, right? Free of complex tasks on the individual routers. Okay, because individual routers then can use the spare time and computation power to do forwarding, which needs to be really, really fast. Very good point, Sam. And Louise, love Louise's answer. Louise, the only one selected the traditional routing, because the central one is what? Having a big server doing everything. It is. It's gonna be more efficient. So obviously, Louise knows the advantages of the centralized one, but isn't that a central point of failure as well? Isn't it? Right? Bad resilience, exactly. And Pooh also like the modern one because you just have more control, right? So I can see you guys prefer to having more control. Well, you know what? Most of the engineers are like that. And Louise is a more democratic engineer. All right. Hey, there are different types of engineers, just like there are different types of network layer services or transport layer services. Okay. Kaijin likes also the modern one. James also likes the modern one. Is once again we hear easier to control. You have more control. Anthony provides more comprehensive traditional counterpart. Yeah, indeed. Stanley also likes the centralized one. Indeed. Yanjun likes also the centralized one. And this is thinking again, I think some of the earlier students thought that leave the load, okay, to the server, and so that the routers can be faster forwarding packets, okay. And Ivan and William also prefer the modern one, and once again, because you have more control. And it's easier in case there are issues showing up. And Polly, sorry, Polly is a bystander. I can decide. I'm half-half. I like the distributed one because it's cool. Distributed routing algorithm is just cooler. I don't know. Well, when we start introducing the routing algorithms that used to run in the traditional route control plane, you'll see. And there's no central point of failure. So this is similar to Louis' concern, right? So I like the distributed one. I like the traditional one. I like, however, also the modern one. This is why today the routers on the internet, there are still a significant number of them not yet doing the centralized server, the SDN routing. Okay, so they are not exactly the SDN routers. They are still the more traditional routers. All right, good. So this is a very good exercise so that you guys, hey, get some sense of the advantages and disadvantages of either kind. And now we can move on to the second video related to the network layer service models. And this is about, hey, in the network layer, designing a general network in a way, there can be more than just two services, connectionless, connection-oriented. One can actually define more layers of services, especially if you are choosing the connection-oriented service at the beginning. One can actually design more layers so that you can provide services in finer granularity, and that is what this video is about.
Yeah, those are the major CAMs. But within each CAM, you can probably define finer service models so that you provide different levels of service. So, for example, okay, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, or we restrict the time differences in between these packets when they arrive. So again, yeah, the service models, they can be finer or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time in ATM's case, and continue to be used today on the internet as well. So the internet service is, yeah, the best ever. So essentially, it's not guaranteeing anything, no guarantee at all, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer, between the TCP sender and receiver. Now ATM, quite sophisticated, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. So this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. So you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now these two, however, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee. And in this case, no longer a congestion signal going back to the data source. So you see, again, network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, there's just one model we talk about, the best ever.
All right, now we move on to talk about routers. You will see in this video the components in a router. There's of course a part that's doing the forwarding, and that's the part that's switching packets really fast. And there's a part that is contains a processor that calculates the routes. And then there will be a bunch of these incoming interfaces where the packet will arrive into the router. And of course, there will be a bunch of these interfaces for the packets to exit and connect to the next routers. Okay, so router architecture, pay attention to the video.
Now let's take a look into the inside of a router. This is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. Okay? And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay? By output ports, input ports, I actually meant that these network interface cards, okay, that we use to connect to the routers that are passing data in, passing packets in, as well as connecting to routers, okay, that we pass the packets out. Okay. Now, you see then, yeah, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, yeah, the computation, the switching there is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay, for example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, the one most important functionality for the router to do is forwarding. Now, it also does route computation here. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface here. Let's zooming a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay. So what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay. So the forwarding of packets coming into each of these input port is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet, okay? And it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. So the goal here for the incoming network interface is so that it can complete the input port processing, the lookup forwarding at the line speed, okay? Meaning, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. Okay. If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we will end up having this. Okay. Packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queuing delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. Okay. So it's a lot more general. But you can also see that provided the same lookup processor, okay, this is going to be a bit faster and this is going to be a bit slower. So in order to keep up the speed, okay, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, okay, these SDN routers will need a faster lookup processor here. So this one here, SDN routers, more expensive, while this one here, usually more affordable.
Yeah, I know. If I ask you which one is going to be more affordable, and I guess the answer is more obvious, the traditional one. Okay. And so at the end of this video, you hear something that's very important. We talked about the routing part. There's the traditional model, distributed route computation. The modern one, centralized route computation, concentrating on a big server. You know what? Forwarding function there, you hear. There are also two ways. The traditional one, is only based on the destination IP address. And the modern one, working in also the software-defined network router, is the more generalized one. So you can actually forward packets not only on its destination IP address, but also other fields in the packet headers. So more general. Good. Now, next topic, very important. Pay attention because quiz 33 and 34 are directly related to it. That forwarding process is about looking up, for example, the destination IP address to a table. And in the table, you will see a bunch of different destination IP addresses. And the answer of the lookup is which network interface to go out next. That is, given a packet arriving, look up the table, find what is the next router to go. And that matching process is called the longest prefix.
So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Okay? Destination-based forwarding. Okay? As you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. Okay? So if the destination address says this, 11001000, matching this guy here, then we take this output port, okay, output link interface. If it matches, for example, this IP address, okay, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this is this particular destination's output interface being 0. So in fact, okay, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface. For each of these IP addresses, what is the output link interface? But the thing is this. Okay, how many possible destinations there can be? Well, the IP address is this big. Okay, the IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. Okay, and each entry might require, you see, 4 bits. 4 8 bits. That means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that would be 5 gigabyte at least, just to keep the forwarding table. Okay, so the input port network card there, okay, it's gonna require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually, expand the IP address space. So this is a 32 bits IP address. This is IP version 4. Later on, you'll see. Okay, there's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry, is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing table lookup is to do matching, but we are only matching to the longest prefix. Okay. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay. This time we don't have 1 entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. Okay. So that is also saying that as long as the destination address, the first few bytes match this pattern, Okay? The rest of the IP address can be general, free. Okay? Now, as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Okay, now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. All right. So let's exercise a little bit. Now, if we get a packet, the destination address is this. What should be the output interface? Let's see. The first 8 bits match. Great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, yeah, the first 20 bits are all the same. So these two destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these two not matching. Therefore, this packet goes to interface 0. Now, the second destination here, 21st bit is 1, so it should be either one of these. Now, 000, well, it actually matches more the second entry, therefore, the outgoing interface for the second destination address being 1. And that takes us to a double quiz time.
All right, double quiz. And you know what? Yeah, quiz 33 is very similar to the example we just showing the video. And I'm asking you that we have now 4 packets, Q1, packet 1, Q2, packet 2. And this is the sequence of 0, 1 bits. And we'll match to these entries in the routing tables. So maybe let me go here. Yeah, so this is quiz 33. Yeah, and this is our forwarding table. Okay. So for each of the packet here, find what is the outgoing interface, 0 or 1 or 2 or 3. Okay, good. Let's go to the Discord space. Yeah, I see that, again, as I said, this one is straightforward. Okay, so some of you guys have already looked it up and find that Q1 is interface 3, Q2 interface 2, 1 and 3. 3, 2, 1, 3, exactly. Okay, very straightforward, as you can see. All right, so all of you get the bonus. Very good to see that you guys are following the lectures. Great for you. And while some of the teams are typing up your solutions, let's go to quiz 34. But you see that it's already 2:13. Even though this one is just as straightforward as quiz 33. Let's make it take home. So if you guys have a bit time, feel free to stay a little bit during the off hour. Off hours, of course, to finish quiz 34. Then you need to worry about submitting all the solutions by Saturday. Okay, and 34 is this. 33 is asking you, if you have packets coming in with these destinations, what is the outgoing interface? This is asking you to, hey, we know for all these destinations, they're supposed to go to the interface 0. Can you somehow write the prefix of a whole bunch of IP addresses? So let me come here to quiz 34. All right, so here's a bunch of IP addresses. For these destinations, they should all be forwarded to interface 0. But can you somehow write these bunch of interfaces in just one prefix? Okay, so if I may, let me demonstrate. Hey, these are all the same, right? These are all the same. These are all the same. Things begin to differ from what? from this bit and on. So only the last 6 bits differ. So you write all the way to here, and then you do star, 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 6 stars. Okay, that's the first entry in your forwarding table. What will be the second entry? And what will be the third entry? So this guy, write them in also the prefix format. And there should be 4 entries because, hey, the otherwise here is still 1 entry. Good? Yeah, I guess you know what to do there. If you go to the Discord space, yeah, I see Sherman already write something. Let me see if you are correct. You know what, Sherman? You are 100% correct. Yeah, so the first entry matches all the way to the last octet and the first 2 bits of the last octet. So that's 26 bits matching, right? And this is matching a 19 bits. And this is matching 8, and then 7 more bits. So that's 16 plus 7, 25 bits. 23 bits. All right, good. Yeah, Anthony, you're right. So the last entry is, of course, otherwise. Very good, guys. So congrats to team. And Sherman, which team are you? There you are. So team 13, 9, and 1. You guys have completed all the quizzes this week. Congrats. All right, so that's all for today. And tomorrow is exam 2, all right? And so with that said, I say goodbye and I see you tomorrow. So all you need to do tomorrow is join the Google Meet session. And later on, you will see the link for the Google form. And you, when I turn on, then you can start working on the exam. Okay, so with that said, I say goodbye. I see you tomorrow. Okay, bye. Okay, Louis said 13. 13 for what? 23, right? Bye, guys. Yeah, bye, guys. So for the exam 2, guys, the best way to think of it is this. You just try your best. Just try your best. There you go. There you go. Just try your best. So 26 bits, 19 bits, 25 bits. Very good. Team 15, great. Team 20, perfect. Team 6, wonderful. Team 10, very good. Team 12, perfect. All right. See here? Team 20, perfect. Team 12, perfect. Yeah. So maybe bubble tea? Yeah, sugarish food is comforting. Yeah, comfort food. Okay, good. Okay, bye. Okay, bye. See you tomorrow.